All right, good morning, guys. It's Monday. We're going to be talking about transformations, specifically our reflections and dilations of all the different parent functions you learned on Friday, okay? So hopefully you're good with the parent functions, the translations up, down, left, right. We're going to dive into the reflections and dilations today. So first off, pause this video, give you 5 seconds, see if you can answer this question. Okay, so if we looked at this question, I'm going to show you how to do this using DESMOS to check your answers. Okay, you won't be able to do this because you will not be able to plug this in a calculator, but let's use this to kind of explain what's going on. All right, so if I look at my function, okay, and so over here in DESMOS, you can write piecewise functions. You'll learn more about that tomorrow using the same type of set notation, but DESMOS works a little backwards. They want you to give the interval first. So we said from -1 to 2, and then you put the equation after a colon. That's how DESMOS works. All right, so using that, if we have our equation, we are going from our point down here at -1, -12, all the way up to 227. So what is the rate of change from -1, -12 to 227? So we are going up, so we know it's positive. How high up are we going? We are going up from 12 to 27. That's 39 over the course of 1, 2, 3. So up 39 over 3. Well, we all know that 39 divided by 3 is 13. So we should have gotten our answer as D. Okay. Moving right along, put it back to there. All right, now let's get into what we're talking today. So reflections. All we're doing is we're taking whatever our basic function is, and we're flipping it either up and down, okay, so over the x-axis, or we are flipping it left and right, okay, over the y-axis. So right now, your book's giving you this beautiful little graph to help explain that. When we reflect over the x, so I'm talking about from top to bottom, I am going to put a negative on the outside. So anytime I plug that negative, I'm going to reflect over the x-axis. Same thing using function notation for the y-axis. If my negative is inside the parentheses, now I'm flipping over the y-axis. Okay, so left flips over the right. Okay, so that's what we are talking about. You can see this in DESMOS here. All right, so looking at this, we've got our function here, f of x. Hopefully you all know what that parent function is. It is a square root function. So f of x is a square root function. And here's what we're going to do. First, we're going to take our function and flip it over the y-axis. So that means my new points, a goes to 0, 0 as a prime. B goes to -1, 1, and C goes to -4, 2. So we've basically just changed those values. Now what happens if I was to flip it over the x-axis? So now all of my original points go to new points down here. Okay, so A goes to A, stays in the same spot. B flips, C flips, okay? And so that's what we're talking about when we're talking about reflections. We are flipping over lines. All right, so in looking at our parent function of a square root function, the square root of x, describe how these two are related. So I'd like you to look here. How do we go from f of x to g of x? Well, it appears we are going to have to first do something and then do something else. Hopefully you remember your order, but let's talk about it. Can we first flip this up and down? So if I flip it over the x-axis, I would have a graph that looks like that. Now, does that match up with our original? Well, no, not yet. We need to do something else to it. We need to shift it to the left. So words-wise, you might say something like, I need to reflect it over the x-axis, and then I need to shift it to the left. But how do we write that? Okay, the way we communicate that in math is a reflection over the x-axis puts the negative in front, so the negative goes in front of our original square root of x, and then a shift to the left is opposite what we think, so your x's always lie to you, so anything that is inside the function's base, okay, surrounded by the function, this one is a square root, anything inside here is lying to you. So instead of it looking like it goes right, it's actually going left 1 unit. Okay, and you can see this again by plugging it in DESMOS and checking out our shifts here. So if we were to take everything in this guy and we were to shift it, okay, we would make a negative reflection and then shift it left 1 unit. Okay, so that's what we are doing with that one. All right, moving along. Now let's give you some chances to kind of graph some of these things. So first I'd like you to graph f of x. So what axis is our function going to be reflected in? So we're going to sketch this in one color and then we'll reflect it this way. Hopefully you know what that negative does. And then we'll write that new equation based off of something we did. Okay, so the first one, we know this is the parent function. Y equals x squared. It's going to look like a nice, beautiful parabola. We'll see if I did it perfect here. Okay, and we're going to take this and we are going to, I'm going to copy it. Let's change the color to a different color. And I'm going to reflect it. So the question is, are we flipping it left and right to where it would kind of match back up? I did okay. Obviously not perfect. Or would it, let me flip it back. Would it be better if it flipped up and down, up and down? So now it is reflecting over the x-axis. So what does that reflection over the outside look like? Well, let's show you. If I were to reflect it, boom, it's reflecting over the x-axis. So anything on the outside is just heads up, it's flipping up and down. Okay, so that is a reflection over the x-axis, up and down. So the new equation, what would that look like? How would I write that equation of the red function here? Well, that would be just a reflection, negative x squared. Okay, basically you're going to take the original f of x, that's everything in red, and you're going to make it negative. So there's the original, and you made it negative. Let's try another one. This time we're going to take the square root of x plus 2. So we know that plus 2 is actually a lie. So it's moving us to the left 2. So it'll go over 1, up 1, and then 1, 2, 3, and then up another 1. So it'll be at that point. And so I'm going to sketch this one here. It's half of a parabola, right? So that's what a square root function is, but it has to be a function, so we restrict it. We can't look at the other half of the parabola. Okay, because this half we can't show because then it wouldn't be a function. So a square root function, we're only looking at half. So that's in green. Now we're going to reflect this whole thing, but instead of it being on the outside like this one was, we're going to reflect it over the other axis. So that means every point is going to flip over our y-axis. Okay, so let's show you what that looks like in DESMOS. Test it, make sure we're good with our reflections. So if I was to reflect it over the y-axis, okay, my points would reflect over the line when x equals 0. Okay, so that line right there, hopefully you see it showing up, that is when, or what we would reflect over. Okay, so that's how I do it. Now, algebraically, how do I write this? Well, we're going to take negative x and plug it in everywhere I see x. So let's try that. Square root of negative x plus 2. Now, in doing this, we have to remember a key concept of factoring out a b value. Okay, anything that is underneath our square root symbol, okay, we want to factor out and get x alone. So how do I factor that out? I'm going to take out a negative 1 from both of these. So if I was to do that, now my b value is a negative 1. Okay, if I took out negative a negative 1, I'll be left with x. If I took out a negative 1 from a positive 2, I'd be left with a negative 2. Okay, and so now that is how we could write with a b value of 1. In math, there is some invisible math. We don't have to write the number 1 because everybody understands when you're multiplying by 1, you are yourself, the identity property. So because of that, we'll actually just write it negative x minus 2. And this is going to be easier for you to see. Oh, well, my red one, the minus 2 is actually a plus, and that's why it shifted from the vertex 2 units to the right. So this would mean 2 units right, and this would mean reflection over that axis. Okay, let's try one more or two more here. Why don't you pause the video, see if you can do these. When you come back, we'll talk them through. Give you 5. Okay, in the first one, so let's look. We've got a reflection, and then, oops, got to factor out again. Okay, so let's factor out a -1, and then that would leave me with x and a +2, all underneath that square root symbol. So we know there's a double reflection, no stretches, dilations. We're still just dealing with reflections, and we've shifted to the left 1, 2 units. So our original function, right, this guy, has reflected and reflected. So let's try a double flip here. I will flip it up and down. I will flip it left and right, and I will shift it. Instead of being on the origin, okay, instead of being on the origin, we've actually moved to the left 1, 2 units. So let's check and see if that's what it looks like. So there's our original, which is the same thing as when we wrote it factored out, okay? So it looks like we did a good job graphing that guy, okay? Order's not important yet because we haven't introduced compressions and stretches. So right now, you're kind of thinking, oh, order's not important. It is. You'll see it later. Okay, let's look at the next one. So the next one, how do I write this equation? So what is the parent function? We know this parent function is y equals the square root of x. If I was to graph that, I start at the vertex, 0, 0, and it's just half a parabola. So I go up 1 over 1, up 2 over 4, up 3 over 9, etc., and that would be the parent function, y equals the square root of x. Okay, but we've obviously reflected and reflected again, so we're going to have 2 reflections, and it doesn't look like any dilations because we're not into that yet, so not applicable. But we did shift, and we're going to shift this direction. Oh, sorry, that direction, 1 unit. Okay, so let's talk about it. I'm going to take my green function. I need to, let's flip it over up and down. So it would have flipped to here. Then let's flip it left and right. And that would have flipped to here. And then it looks like I need to shift the whole thing over. Boom, 1 unit. So we did a double reflection. So we reflected over the x, over the y, and shifted to the right. So how do I write that using normal notation? So h of x, you're going to be negative square root of negative x, and then how do I say it shifted to the right one? Remember, our x's lie, so it's a -1. So that should be our equation. Let's check it. All right. Ooh. So this one, I gave you some values you can play with. So we said our a value, remember, we're not stretching or compressing, so that is 1. Our b value, same thing, not stretching or compressing, that is 1. Looks like we said we shifted to the left or the right. No, our c value is actually 1 there too, but our d value, we didn't go anywhere up or down. I guess the only thing we needed to change is our reflections, so I would need to make that a -1, and I would need to make that a -1. And then let's check. Okay, so do we have that same original equation there in red? Yes, we do. Okay, so what was my a value? Should have been a -1. Did we get that? Yes. B value -1. Yes. C value +1. Yes, because it's opposite, right? Lies to you. And then D value is nothing because we didn't go up or down. Okay, so that is reflections. When you come back, click the next video. We'll talk about your dilations and our stretches or compressions, both horizontally and vertically. All right, guys, good stuff on those reflections. Now click the video.